Okay, this is the first video on Chapter 6, which is the chapter about energy. I'm going to start with just kind of some basic concepts around energy, and then we'll move on to the chemical aspects afterwards. So, as we all know, energy can take multiple forms. Energy can take the form of an object that's fighting against gravity, meaning it's up high, and it's therefore at a higher energy state because once it falls, it will actually give up its energy. Its potential energy that it had against gravity. An object in motion will have what we call kinetic energy. That's energy just due to the fact that it's in motion. And as we've kind of been talking about a little bit, is that even substances have inherent energy in them, because if they were to react chemically, they may actually give off energy later. And that's actually kind of where we'll take this back to when we talk about the energy aspects with respect to chemistry. But a few things first. I got a picture here that depicts a weight that actually has potential energy because it's up against the gravity well, meaning it's high, it's high up in the air, 10 feet up in the air, and you can see it's kind of positioned to fall and land on this fulcrum here, and there's another weight here which when this thing falls, the weight will go up in the air. So what we have here is, first of all, I'm going to describe what the system is here that we're talking about. And that book is careful to describe the difference between the system and the system's surroundings. So in this case, the system that I want to define is this weight up here, actually this weight here and this weight here. Basically the collection of the 10-pound weight and the 5-pound weight. So at its initial state, the energy of the system can be kind of measured by the fact that we have 10 pounds up 10 feet high up in the air, and there's a certain amount of potential energy there. Meaning if I were to actually take this 10-pound weight and have to move it up 10 feet, I would have to expend 10 pounds times 10 feet of energy, which is 100, and the units here are foot-pounds. Kind of an old-fashioned measurement for energy, but it certainly works still, and it's fitting for this drawing. So, and then this 5-pound weight, well, since it's sitting at a height of, let's say, 0 feet off the ground, it takes nothing to. It has no potential energy with respect to the starting point. Now, of course, this starting point could be up on a hill, in which case we had to carry the 5-pound weight up the hill. But let's imagine that's not the case. That it's just sitting here at on the ground. So the total energy in the system is 100 foot-pounds and plus essentially 0. When this weight drops, and it drops and it hits this little fulcrum here, and it ends up on the ground here, well, underneath the fulcrum, which of course is now going to be slanted the other way. This 5-pound weight is going to shoot up into the air. Okay, so when it shoots up in the air, let's freeze time. Let's imagine it goes, this high, and then stop. And now let's inspect the energy of the system. So first of all, the system, our system, which is defined as the two weights. Put this 5-pound weight up here with those two weights. We've lost 100 pounds. So the initial state had 100 foot-pounds. And the final state had essentially how high this 5-pound weight flew up in the air. Let's imagine it flew up in the air 8 feet. Okay, so the final basically has 5 times 8 equals 40 foot-pounds. So it looks like we lost energy here. Okay, well, what the first law of thermodynamics says is that you can never lose energy the universe never loses energy. So when your system, however you defined your system, in this case we defined our system as having these two weights, the system as we defined it actually lost energy. We started with 100 foot-pounds, we ended with 40 foot-pounds, meaning this weight up in the air. Where did the other 60 go? Well, the other 60 were essentially lost because what happened is, I would say differently. It was lost to our surroundings. So the system lost the energy, but the 60 foot-pounds had to go somewhere, because again, the law of thermodynamics says is that in the universe, any transaction, the energy remains constant. So in this case, our system of the 2/8 lost energy, but where did it go? Well, it probably made a bang sound when the weight hit the fulcrum. This fulcrum probably heated up as the process of being hit by the weight. Sorry, I kept saying fulcrum. I meant lever. The fulcrum here probably actually got hotter as well because there were some frictional losses as the lever tipped over. And of course, as the weight is flying up into the air here, it's also moving against air, which is essentially heating up the surrounding air as the weight goes up. And of course, even as this weight drops, it was probably heating up the surrounding air a little bit as it dropped. So we had a bunch of energy losses as we defined the system. But again, as a whole, putting a bubble around the entire system, the fact that weight dropped like this didn't change the energy of the entire system at all. Okay, so that's one of the things that we talk about a lot in these discussions, especially when it comes down to chemistry, is we talk about heat gains and losses with respect to the surroundings of the system that we're talking about. Okay, all right. So that was just kind of a basic thing showing work, and also kind of introducing the fact that energy can have multiple forms, and even in energy transfer, like in this case, the transfer is kind of twofold. One is in the work that was caused on this weight, but then the rest is essentially lost as heat. Okay, and this is actually kind of where I want to take this subject, is that basically energy transfer, basically the changes of energy in a system are primarily, you can think of them as really exactly two sources. So essentially the total energy of the system, it can be thought of, or let me say differently. The energy change in a system is equal to essentially the change in heat plus the change in work. Okay. So again, in a system we have with these weights, we actually generated some work by kicking that other weight up in the air, but then the rest of the change was kind of lost to heat. Okay. Now, in essentially the terms, when you boil this down into kind of real thermodynamic terms, we actually call this heat component, we use the letter H, and that stands for the word enthalpy, which again is a thermodynamic concept that refers to the disorganized energy in a system, essentially the energy that's not related to work. And then this other, it usually is called work. I think it actually has another symbol, but is it the W or is it, I can't remember what symbol it usually is. Yeah, usually it is W. And then so the W is the rest of the work. Now, this is just a long-winded way of saying when we're talking about an energy of a system and we want to look at the energy of a system, primarily, especially the chemical system, in many chemical systems, the amount that work contributes is really small, or a lot of times it's zero. So you can think about when we're talking about enthalpy or enthalpy changes in a system, we're essentially talking about the change of the total energy of the system we're talking about. And so we're actually going to use this concept quite a bit, and we're going to kind of use it interchangeably with the word energy. And this will be the last time that I show that it's not exactly the same as energy, because sometimes there's a work component to it. Okay. I think in the next video I may have a practical example of this as well, but I'm not sure if I'm going to cover that next video or not. Maybe I should do it now. Yeah, sorry. I'm going to erase this little chessboard and I'll redraw that for the second video. Okay, here's a practical example that involves chemistry a little bit. Oh boy, can I possibly draw a piston? I will try. So this is a piston in your car, and here is the cylinder. And in this cylinder, actually I should draw the piston a little bit further down. Well, I'll just draw the cylinder a little bit bigger. So if we have a cylinder that's like this big, let's say, and we introduce oxygen and nitrogen, and we introduce gasoline, which we'll just kind of abbreviate as C8H16 at the moment. Okay, and we introduce a little bit of this organic compound and this gas into this cylinder, and we ignite it. We basically cause a little spark to happen, which causes this to burn. Now again, we've looked at the chemical reaction of organics and oxygen before. As we know, it produces carbon dioxide and water. But, and of course, it also releases quite a bit of heat, as we said. Of course, it releases energy. I always said heat, but in reality, when these components react in the cylinder, not only is it heat, but when it reacts, it produces those extra gases, carbon dioxide and water, which of course forces the cylinder to go in this direction. Basically, it explodes and pushes the piston up, which of course this piston, when it gets pushed up, is connected to your drive shaft, and that explosion actually results in work that propels your car forward. So in looking at the system, which let's say now contains everything that we're seeing here, the energy change of the system needs to take into account that we actually generated some work. We also generated quite a bit of heat, in that these gases, when they got put in here, were at one temperature, but after the explosion they were at a higher temperature. So we generated some heat as well. So we generated work and heat, and all we've kind of lost from the system is that instead of these high energy compounds like gasoline, we now have low energy compounds that were produced in the chamber, so essentially carbon dioxide and water. Okay, so the system got hotter due to the heat of the explosion. The system also generated work by pushing the piston, but the system lost chemical potential energy, essentially by converting a higher energy compound into lower energy compounds. So this is maybe a visual way of seeing now why it's okay to basically describe chemical components as having either a high energy or a low energy. Essentially means that when they react, if they're at a high energy, when they react, they're actually going to give up or produce energy that's going to go towards our surroundings. That energy could be in the form of heat and work, or just heat, or just work even. Usually it's not just work, because that doesn't usually happen. There's usually at least some heat losses. Okay. And again, what we use in describing the term that we use to describing this are enthalpies, basically this H component of the chemicals themselves. Okay, that's all I'm going to do on this one, and we'll pick up in the second one